Good morning or afternoon, everyone. My name is Scott Phuong. I am representing DMTF today, but I am part of Cisco Systems. I am a principal engineer, and Brett, go for it.
Thanks, Scott. I'm Brett Henning. I am a software architect with Broadcom and also representing DMTF today.
So today, the both of us are going to present to you SPDM, a Security Protocol and Data Model. And we will talk about how the reasons for SPDM and go through essentially the major features of 1.0 and 1.1 and have a small discussion of how that fits into storage and SNIA's architectures overall. So at a very high level, why did we come up with SPDM, Security Protocol and Data Model? Essentially, on a platform, we were very worried about certain attacks, especially when the threat landscapes and attackers become more sophisticated. They start launching or carrying out physical attacks. That is essentially physical attacks against the actual hardware, right? And as you can see in this picture, that we broke it down into certain types of attacks. We have attacks. If you can see here, we have attacks at the circuit level. You can have, exploitations on your various buses, SPI, I2C, especially those simple buses. They are very easy to implant devices that eavesdrop or manipulate data over these wires. The other reasons we also are concerned about is about supply chain integrity, making sure that as each component goes through the various manufacturers from actual fabrication all the way to the actual building of the platform, they go through many transfers through different manufacturing sites. They get shipped and then they get carried, and you have various shipping agencies. So there's just a bunch, on numerous amounts of people, parties, that play in the whole supply chain, and that is an important part of why we came up with SPDM, is to defend against essentially these two types of attacks. One, again, physical and supply chain. Some of the risks, if we hadn't done this, some of the risks that we would have encountered was, leakage of sensitive information, even manipulation of those information, insertion, some eavesdropper or counterfeiter, so to speak, or trying to perform activities on that platform to gain essentially information that is of great value to them. And so at a very high level, how does SPDM sort of address this? And this picture here shows essentially 6 important aspects or components of SPDM. I would think of it, I understand that this picture sort of lays it out, sort of a flow diagram where, one could infer that, you're supposed to perform steps 1 first and then steps 2. But what's more important here is that these are really sort of 6 different features or functions that address various aspects of a component's integrity. One, you can think of what is highlighted as 1 and 2 being really about capability discovery and device discovery with respect to SPDM, what SPDM is capable of. 3 is about how we do authentication, device identity, device identity authentication. 4 is about how we perform runtime integrity checks or essentially firmware measurements. And then 5 and 6 is really about how we secure data as it transfers over the wire, how we protect that wire, and so on and forth. An actual implementation may follow certain paths. They don't necessarily follow, you don't necessarily follow 3 and 4, 5 and 6 in that order. Some may decide that what's shown as number 4 here comes a lot later on. But essentially, these are the 6 major, I would say, functions of SPDM that help, when you implement SPDM as a whole, help you protect against those physical attacks as well as ensure supply chain integrity. Brett will go over essentially certificate-based authentication and firmware integrity. I will go over key exchange and secure encryption later on. So at this point, I will hand it over to Brett.
So I'm going to go through a presentation that covers some aspects of SPDM 1.0, and this gets into a couple of the points that Scott talked about with firmware integrity and certificate-based authentication. We're making the entire slide set available, and so, but I'm going to be using just a few select slides. So the first thing that I wanted to show was how SPDM is designed to interoperate with other bus protocols. In this slide, we're specifically showing how SPDM was designed to bind to the MCTP protocol, and it did come out of DMTF and the PMCI work group. And so it was designed to actually use a new security message type, so type 5 and then type 6 as well. And it uses those message types to bind to the existing MCTP message layer. That being said, there are ways to bind to other protocols as well, and towards the end of the presentation, we'll get into some of those. So this is a higher level, actually I should say more detailed flow of messages that show up in SPDM. This assigns message names to the message types that Scott had mentioned. And these messages take us all the way from discovering the capabilities of the two endpoints through negotiating, so setting up how they're going to communicate with each other, and then getting into a challenge and measurement exchange. And I'll get into what those are. Those are the two that I'll be covering in here. As you can see, we have a number of different messages that are actually spelled out in detail in this slide set as well as in the specification. And I encourage people to dig into this when you have more time than our 20 minutes allows today. This first message I wanted to highlight is the challenge exchange. And in this message, we see that the requester sends a nonce as well as a challenge request to the responder. And the responder has to sign this response along with a hash of all messages that have happened, that have been exchanged up to that point. And it has to sign all of that with a private key. And by doing this, the responder can prove its identity. And specifically what we mean when we say that is it can prove that it has knowledge of the private key that was exchanged with the requester. The other one that we wanted to show was get measurements. So measurements are just a way of exchanging a hash between the two endpoints. And in this case, and the hash can represent essentially anything that the responder needs to represent. So that could represent a firmware image or a set of versions or perhaps a manifest of multiple measurements. And so we see again that there's a message and some number of measurements can come back in the response, and then those measurements can be signed to prove that they came from the responder itself. And now with those covered, I'm going to turn it back over to Scott, who's going to go through some of the newer features that came in SPDM 1.1.
Thanks, Brad. Okay, so in 1.1, we bring in pretty much one important crucial feature to really create a pretty comprehensive security picture, and that is what we call session key exchange protocol. It's not a new protocol, it's still SPDM, but it's how we establish a session for SPDM or a secure session. What secure sessions are used for is to transfer any data over what I call in the box wire, and to protect it from eavesdropping or manipulation of that data. So key exchange, this protocol at a very high level follows TLS 1.3, the closest. We base it off of TLS 1.3. So this how we establish a secure session is very, very similar in many aspects to TLS. We do, and just as Brett sort of shown you earlier, as you start and build that session, the first thing you want to do is to be able to prove your identity. That's what 1.0 was to prove that you are who you say you are. So that's through that X509 authentication and the challenge requests and challenge off response that Brett showed earlier. And then from there you could do firmware measurements if you wanted to do further integrity checks before you decide, hey, I want to start sending whatever data, which we in SPDM call application data. Is just a generic name to express higher level data. It could be MCTP data, it could be storage data, it could be any type of data. But SPDM is what helps you create that session in order to protect the data as you send it as it goes over the wire. So one of the things that we do, so if just like TLS, one of the things that we do is we want to be able to create we want to do a key exchange, and key exchange includes key confirmation, and what that really means is that you're trying to share a key without actually sending that key over the wire, because if you send the key over the wire, there are certain security risks about it, and thus the question becomes: how do I create encryption keys without sending it over the wires, and somehow both the requester and responder are able to figure out and come to the same answer as to what that encryption key is. And the way that's been done and traditionally been done is through what is called a Diffie-Hellman exchange. So key exchange exchanges the public portions of that Diffie-Hellman as you may already know, Diffie-Hellman is an algorithm for computing and deriving the shared secret. So once as you do the key exchange, both of you, the requester generates a random number Diffie-Hellman, a random Diffie-Hellman key pair and sends that public key portion. It is an asymmetric algorithm. So likewise, the responder should also be randomly generating a Diffie-Hellman key pair and sending to the requester the public portion. And from there, the Diffie-Hellman algorithm then is able to compute a what we call inside SPDM a master shared secret. So we don't use one thing that we don't do here is use your identity key pair that you use to do the challenge off to establish your identity, because one thing that's new in TLS is what we call forward secrecy. Because if we were to use your identity key pair, and that key pair gets compromised, then all your communication moving forward between that requester and responder would be easily seen and manipulated because of that. So that's what forward secrecy is to separate the two functions, and therefore you use different algorithms, different key pairs to do those two different functions. But after that, you go through a handshake, which is not really shown here. Again, you look at SPDM for more details, but essentially you go through a handshake, which tells you how to derive more encryption keys that are used for your session. Essentially, you start deriving what is a directional specific encryption key that you will ultimately use for communication in that direction. So a session key. So after deriving your master key from the Diffie-Hellman, you actually derive more keys. And it's those additional keys that are actually used to do the actual encryption of your packets that go over the wire, of your data that go over the wire. And then there is a key schedule that you follow so that so both the requester and responder derives the same keys moving for that particular session. That is essentially the one portion of the key exchange that came into 1.1. The other we brought in is what we call pre-shared keys. Pre-shared key is essentially between the requester and responder, you shared the key before you establish the session, and you shared this key likely in a secure manufacturing environment. So it's way before the product even shipped. It is likely that this key is shared and provisioned or into the requester or responder before it reaches the final user. So that's what we mean by pre-shared. It is not a dynamic pre-share. It's something that's been provisioned likely in a manufacturing environment as the product is getting built. So that's what we mean by pre-shared. And the key that is shared is often a symmetric key. So that's why you should provision that secret in a secure manufacturing environment. Now, the reason for having a pre-shared key option is to ensure simplicity for especially devices that can't really do a Diffie-Hellman and don't have random number generators. I would say a more resource constraint type of device. But again, the idea here is that you still establish a secure session, but instead of doing Diffie-Hellman exchange or doing that complex Diffie-Hellman math, you already have a symmetric key that's already been provisioned device, and from there the responder and requesters derive keys from the same key schedule as you did for the previous case. But essentially, that's the point where everything becomes consistent, is the derivation of additional keys. But once that is done, then again, once the secure session is established, any data, application data, can be transferred over that wire and have encryption and message authentication protection. Okay, so that's essentially what that is the biggest addition to 1.1. Okay, from this point on, I'll hand it back to Brett, and he will give further insight on how SPDM can be used in a storage scenario.
Okay, thanks, Scott. So just a couple slides about how SPDM can be extended to storage. So this shows a high-level overview of a system architecture that has a root of trust, a device in the middle, and then a storage bus. So this should be a pretty standard scenario for most people. What we would see with SPDM in this type of architecture is, yes, you would first establish a session with the device itself. So you go through all the steps that we've described up to this point. And then you would work with the device to enumerate its attached devices, and then send SPDM commands through that device out to the devices on the back end. So that would, in most systems, look like a situation where you would shift from an MCTP type bus to a storage type of bus. Now, how does that happen? Well, there has been spec work in this area. So SPDM is being added to a variety of storage protocols. It's being done through the security command set. And so referencing the SCSI commands, it's in the security protocol in and out. And there's a command code, E8, that is used for SPDM. And this is expected to be extended to other storage protocols that support the security commands. And that is all for our talk today. Thanks for joining us, and please rate the session and post any questions that you have. Thank you.
Thank you.